Hello all. So in this tutorial we will start the design of our neural network. So first of all we are going to design a basic neuron, which is the basic building block of a neural network. Okay. So again I am referring to that same website here. So this is the general architecture of a neuron. So you can see many inputs come to the neuron. So these inputs again, depending upon our application, it can be some pixel value, it can be some sound sample, things like that. And what the neuron basically does is it will multiply each of this input with a corresponding weight value and add them together and add a so-called the bias value to that, and finally apply to an activation function and gives us the output. Okay, so that's what is represented here. Assuming it is using a sigmoid activation function, the output is 1 by 1 plus e to the power of minus z, and where z will be this value w dot x. This is a dot product. That means each input is multiplied with the corresponding weight and add the bias. Bias can be positive or negative. Okay, so add with the bias and gives the output. This is what basically a neuron does. So you can see like the architecture, it is very hardware friendly, especially this dot product, because you can do this multiplication and addition in parallel in hardware. So it is supposed to be much faster than software, but we'll have to do some kind of trade-off here, because many neurons, it may have hundreds of input. For example, we are going to again implement the neural network for MNIST dataset, and the neurons in the first layer in the MNIST is going to take 784 inputs. Okay, that means if in hardware design, when you are designing it as a module, you will have 784 inputs for representing the input, and each input, again, that's not one bit. Okay, depending upon our fixed point representation, depending upon the value for x, it may be like 10 bits or 32 bits, whatever it is. So those many wires are coming here, and if you try to do that multiplication and addition in parallel, that is going to give us a big combinational circuit. Okay, so you may be doing things in parallel, but the maximum clock frequency at which you will be operating will be so low that you won't get any special advantage. So to avoid it, we will have to make things little bit sequential. Not only that, we want to make a design in such a way that it is quite scalable. What I mean is I should be able to use the same neuron design irrespective of the number of inputs. That design I should be able to use with the 2 input, 10 input, 100 input, 1000 input, any number of input. I don't want to change the design of my neuron. Okay, so in our hardware implementation, you will see the interface will look slightly different, but otherwise internally the operation is same. We will do the multiplication and addition operation, uh, basically MAC operation, multiply accumulate, and we will add with the bias and apply it to the sigmoid function. Okay, so the architecture of the neuron that we are going to design is shown in this picture. Now I will show you the code so that we can have one-to-one correspondence. So whenever you look at the code, look at this picture also, so that you clearly understand what is happening. So you can see the main components here. So we are going to use a memory called a weight memory for storing the weight value. Okay, now the depth of the memory will depend upon number of input coming to the neuron. So each location in the memory will represent a weight value corresponding to that particular input. Now this you can implement either as a ROM or as a RAM. That means, again, as I mentioned before, we are going to use pre-trained network. So the weight values will be already available. So you can just store it in a ROM and you never want to change it. Or again, for flexibility, you can have some provision where this is like more like a RAM, and you can store the weight values here. And later, if you want to change, you will be able to do it. So I will show you both. So both are supported in our design, and this is where our input is going to come. And I have a delay here. Why it is that I will explain. And here is the multiplication operation. We are multiplying each weight with the corresponding input, or each input with the corresponding weight, and that is managed by this logic. He is the one who fetches the appropriate weight from this memory and multiply with this input. So we have multiply operation, and that will go to the accumulate operation, which is basically here. So it will add this output with the previous output. Now here there are some muxes and some additional circuitry. Again, when we look at the code, I will explain them what they are. And this is the bias value. Finally, what happens is this multiplied and accumulated value will get added with this bias also through this adder, and that will be going to the activation function. This is, again, as I mentioned before, is a ROM where we store the pre-calculated value for our corresponding activation function such as sigmoid. And finally we have the output. Okay, so this is the generic architecture we are going to look at. Now I will directly show you the code, then let's try to find out what's happening. Okay, so this is the code for our neuron, for a single neuron. It's highly parametric. Most of the things are parameterized, and as we go along, I guess we'll have better idea what each parameter is doing. Okay, so first thing I would like to show is this memory for storing our weights. So you can see like there is a weight memory here. So that weight memory is instantiated here. This is that weight memory. So basically this is the code for that weight memory. Again, you can see we are not using any Xilinx IP. We are just writing it as a Verilog code. Okay, so this is the memory inside that. Now you can parameterize what is the width of that memory and what is the depth of that memory. So the depth of the memory depends upon how many weights you have. So the number of weights actually depends upon the number of inputs to your neuron. Okay, so these things will be configured from the topmost level module, like how many weights are for each neuron. Okay, so here it is written like 3. It need not be 3 because on the top module it is 784. Okay, so these values depend upon the particular application we are going to look at, so that you can forget for the time being what is the exact value, but overall idea is this: you can configure the width here and you can configure the depth here through this parameter. And this is the part which is basically deciding whether this will act like a RAM or a ROM. So we have a parameter here called pre-trained. It is a defined value which is stored in this include file. Again, I guess in previous tutorials we have never used this include file. So again, coming from our C side, so you can I can show you that file. Forget about everything, only look at this one. So we are defining pre-trained. Okay, tick define pre-trained. So if you define that, this will act more like as a ROM. If that is not defined, it will act more or less like a RAM. So you can see like there are two parts here, which only one of them will be true depending upon the condition that we have written here. Now if it is behaving as a ROM, this is what we are going to do. This $readmemb, that is a Verilog system task, okay, predefined task, predefined function, which can be used for initializing a memory in Verilog. So we already have a memory here, two-dimensional memory that is here, and we need to store the initialization value for this memory in a particular file, and he will read from that file and will initialize this memory. Again, that file depends upon the particular neuron, and it is again configured from the top module, but I can show you the content of one of these files. Okay, so here it is written w_1_15.mif. So this MIF extension, that is something Xilinx specific. It stands for memory initialization file, but that extension really doesn't matter. Okay, you can call it by whatever extension, and even if there is no extension, it is perfectly fine. What is important is if you are writing it as readmemb, that means the content of the file should be in binary format. If you write read mem h, that means the content of the file should be in hexadecimal format. And here you can see it. So these are different weight values for a particular neuron calculated in binary. This is again fixed point representation. How many bits are there and all we will discuss later, but you can see like there are 784 because this particular neuron, it is going to be the first neuron in our MNIST neural network. Okay, and the neurons in the first layer in MNIST, it needs 784 inputs, so there will be 784 weights. So those weights are already stored here, 784 values. And what he does is he will take these 784 values and he will just initialize this memory using that file. That is what is happening if we define it as pre-trained. If it is not defined as pre-trained, that means the values to the memory will be stored by some external circuitry. That is what is written here, which is like our normal RAM. So we have write address bus, and we have write data. This is the write data, and we have write enable, which is like a valid signal. So whenever valid signal is coming, whatever input is coming, we will store it in the memory, and we will increment this also. That incrementing will be done by the external circuitry. It's not done here. That will be done by the external circuitry. So he'll basically tell me where to store the weight, and weight is valid, and what is the weight value. Based on that, we will store it here. That's it for the storing part. Now, reading part is common, whether it is RAM or ROM. How you read is we have a read enable signal coming here, and there is a read address also coming from external world, and based on that read address, and if there is read enable, he will just take that value from the memory and he gives it out. Now here this coding style is important. So remember in the presentation I said like we prefer block RAMs for memory implementation. Okay, now same logic, maybe I can write it in combinational circuit, something like this. Always at star, if read enable, write out equal to this one, else w out is 0. This is perfectly fine. If you don't write this one, that is a latch inference. So we need to write the else case also. Anyway, so this represents a combinational circuit. That means you don't have read latency. As soon as read enable comes, we will get the output. But in the previous case, this is sequential. That means we have one clock read latency. So if you place read enable and the address, the weight value will come only after one clock cycle. Now, if you use a combinational representation like this, Vivado, he will always infer it using distributed RAM. He will never implement this using block RAM. He cannot implement this logic using a block RAM. So if you are intending to use a block RAM, if you want to infer a block RAM, the output should be always sequential like this, and only he will do it. Okay, that's a important thing to remember. Okay, so now let's go back to our neuron. So that weight memory is what is instantiated here. Now let's see how exactly those weights get stored there, provided our neural network is not pre-trained. Okay, so you can see our write address is here. Let's look at that logic here. This is the logic which is basically doing it. So at the top you can see we have this signal again coming from the module on top of this neuron, which we will discuss later. We have signals called weight valid, which is basically saying the input weight is a valid weight, and we have a weight value. Okay, so these are the values which will get stored in that neuron. So you can see the logic here. So at reset, we have this write address. It is initialized with all ones. Again, why it is so, that is because of the particular logic used here. Okay, so you can see whenever we are writing, the write address going to the neuron is current value plus 1. So the initial weight, I need to store it in 0. So for that logic to work, the initial value of write address should be all ones. Then only all ones plus 1 will become 0. And again, since this is parameterized, what is the width of write address is not fixed. You can see here. So width of write address is simply written as address width minus 1. And what is this value? This value is log of number of weights. And this number of weight is a parameter. Again, this $C_log2 is a Verilog task which will find the log of this number to the base of 2. So the width of the address bus for addressing this weight memory should be log of number of weights, right? Yeah, like we usually use. So this guy will calculate that value, and based on that value, write address is calculated. Now, again, these are done statically. That means at runtime, you cannot change this parameter. Okay, these are statically expanded by Vivado when he analyzes your code. So 784 is a constant. From that, he will find this value. From that, he will find this value. But when I write the code, I cannot directly write here like address width. How am I going to write it? All of them should be 1. Okay, so this is the trick in Verilog, those who haven't seen before, to initialize everything to 1 using the concatenation operator. So this basically means replicate 1 bit 1 these many times, which basically means all the bits of write address will be initialized to 1. Okay, for 0, maybe you can just write 0 here, it will just work. But if you want everything to be 1, we have to do something like this when you don't know the exact width. If you really know, like it's always 32-bit, maybe you can write 32 tick h f f f f, something like that. But here, since we don't know what is it, because it's not always a constant, we'll have to do something like that. Now, after that, yeah, whenever there is a valid weight coming from external world, and that is intended for this particular neuron. Again, we have hundreds of neurons, so each neuron will be uniquely identified by few parameters. One is what is the layer in which this neuron is present, first layer, second layer, third layer, whatever layer number, and what is the particular number of this neuron in that particular layer. Okay, based on these two parameters, we will uniquely identify each neuron. For example, this neuron is in layer 1 and this is the first neuron. This neuron is in layer 2, first neuron. Okay, this is in layer 2, third neuron. Like that, each neuron will be assigned a unique number. Again, that happens from the top. Here you can see layer number, neuron number, the default values, but will be configured by the module on top of it. So you can say like this weight bus, it is a shared bus among all the neurons. All of them get the same weight value and weight valid signals, but based on this parameter and this parameter, a particular neuron is addressed. If that is a value, yeah, that weight value will go to win, which is basically going to our weight memory. Weight valid will become 1, write enable, and write address will be incremented by 1. Yeah, since we are starting with all 1, first weight will go to all 1 plus 1 to 0, which makes sense. Okay, so that is what is shown here. So weight value is coming. I'm not showing the control signals, but it ultimately gets stored in the weight memory, and the output from the weight memory is called w_out weight memory out, this one. So next, what we have to do, we have to multiply this w out with the input. So first we will configure the weight, and later at some point we will have the input values coming, which I am calling my input, and there is a value signal also to indicate this is a valid input. Okay, this one. So as I mentioned before, it doesn't matter how many inputs a neuron has, it has only one input bus. So input values will come one after the other. So if you have 784 input, first input will come, then second input will come, so on and so forth, sequentially for each neuron. Okay, so whenever your input is coming, that input should be multiplied by the corresponding weight. Now remember our weight memory, we wrote it sequentially. That means it has one clock delay, one clock latency. So because of that, this input is also delayed by one clock. You can see here. Then it is multiplied with the output of the weight memory. Okay, now you can see each weight will be multiplied by the corresponding input. First weight by first input, second weight by second input, so on and so forth. And here you can see this task again, dollar signed. It's very important. In this implementation, we are going to use 2's complement representation for all the numbers. Now in 2's complement representation, if you just multiply two numbers, the output won't be 2's complement, as I mentioned before. So we need to tell Vivado or whatever implementation tool that we are doing signed multiplication. So use the appropriate circuit to do it. Okay. So what he does is our normal rules. If both are positive, the output will be positive. If one of them is negative, the output will be negative. So he will make the appropriate circuit. He will configure the DSP slices appropriately so that this result, MUL, which is in our figure, this one, MUL, will represent the signed multiplication result of the weight and the input. That's it. So we multiplied it. Okay, so what's the next one? This multiplied value. So this is a multiply and accumulate operation now. Inputs will be coming. We keep multiplying and add it with the previous result. That part is happening here, that addition part, and it appears a little bit complicated. Let me explain what is going on here. First part is easy. Whenever a reset comes or whenever this neuron gives out the output, final output after activation, this sum will be reset to 0. Okay, makes sense. Now these are the other cases. Okay, let's look at the normal case. Okay, here this is a normal case. In during normal multiplication, what happens? So one possibility is that when you do this multiplication and addition, overflow may happen, or sometimes underflow may also happen. Okay, so what I mean is, okay, to clarify it, let's look at this picture. So here, see what is happening. So here you can see a circuit called combo add. Okay, so what combo add does is it adds the current this multiplication result with the previous sum, this sum. Okay, so he's adding them together and you get this combo add. So what is the condition written here? If, look at this bit. So this bit is 2 times data width minus 1. That represents the leftmost bit of MUL. That is the leftmost bit of this guy. If that is 0, that means in signed representation, this is a positive number and sum is 0. Okay. So where is the sum? That is this one, the previous sum. That means both multiplication and the previous sum, they are positive, and combo add, that is representing the current addition between this multiplication and this sum, and its MSB is 1. So again in sign representation, that represents a negative number. So what it basically says is, when you added two positive numbers and when the result is negative, that means something went wrong. Okay, when you add two positive numbers, you are supposed to get a positive number, and if you get a negative number, that means an overflow has happened, and that means the output number is greater than what can be represented using these many bits. In that case, you need to saturate the output. The output sum should be latched to the maximum value. So that's what you can see. The sign bit of sum is made 0. That means it's a positive number, and all the remaining bits of the sum is made 1, which is the largest positive number. Okay, so again we need to refer to this picture to get a clear picture. So sum is the overall output of a particular mux here. Okay, and this combo add is the sum of the current product between input and weight and the previous sum coming from here. What we are checking is whether this is positive, and this is negative. If these two are positive and this is negative, that means overflow has happened. So we saturate this guy to the maximum positive value. Same way the other thing can also happen. See here. So mul ms bit is 1, that means it's a negative number. Sum ms bit is 1, that means that's also a negative number. But combo add, when you added them, here the ms bit is 0. That means you got a positive number. When you add a two negative number, you got a positive number. Again, something went wrong. That is when underflow happens. The output number is so small that it cannot be represented using these many bits. That means you need to latch this output to the smallest value. Okay, that is what is done here. The sign bit is 1 and all remaining bits are 0. That represents the smallest number in 2's complement representation. So this is for taking care of the overflow and underflow cases. If they are not happening, this sum will just represent combo add. So combo add is basically mul plus sum, same as this picture. Mul plus previous sum. Okay, you accumulate them. That is what this part is happening, and that is the usual case when you are doing multiplication. Now, a special case happens when you are doing the last multiplication and addition. So in the last case, what you need to do is you need to add with bias. So you can see here. So generally we add the output of this multiplier with sum, but in the last case, once you have done all multiplication accumulation with the weight, you need to add with the bias value, and this is that value, and that is the case being checked here. You can see this read address. This is the address going to the weight memory. If it is num weight, that is the maximum value, and if the max value is falling, again that logic you can see, we'll see later. Same thing we are checking. This case is for overflow, this case is for underflow, this case is neither overflow nor underflow. We get the sum. So this circuit represents this part except with that overflow underflow logic. So we have a mux which chooses either between the sum of this guy with the previous sum or bias value with the previous one appropriately. And this is a sequential circuit. That means that's also introducing a delay there. So we have this sum. Now where is that sum going? That sum is actually going to our activation function. Now this particular implementation supports two kind of activation function. As of now, you are free to add more. Again, that is where another trick of Verilog you can see using the generate statement if you haven't seen it before. So using generate statement, generally we use generate statement when you have to instantiate same module multiple times. You can use for loop to do it, and you cannot just directly write for loop in your code. You can write that for loop only inside so-called a generate statement. Those who haven't seen it in Verilog before, you need to go and check it out. But here I'm using generate statement to selectively instantiate one of the modules. Okay, so again this parameter act type, that is coming from again from the top, and using that I can choose whether I need to instantiate a sigmoid activation function or a rectified linear unit activation function. This is a linear function and this is a non-linear function. If I choose sigmoid, he will instantiate this one. If I choose ReLU, he will instantiate this one. These are again two separate modules. You can see this is ReLU. It's linear, so quite straightforward implementation. but sigmoid is a little bit more complicated. As I mentioned, we are going to use a lookup table to store those sigmoid values. How it is done, I will explain in the next tutorial, but basically this is how it will look like. We pre-calculate those sigmoid values and we have already stored it. This is also an MIF function, memory initialization function, which is used for initializing this memory. And you can see this sum output is going as the input to this ROM, and the output from that ROM will directly represent the sigmoid value for that particular input. Now, what is that particular input? The MAC output added with the bias value. Multiply, accumulate, you multiply and accumulate all inputs and weights, add the bias to it, and that is what is this sum. That is what is going as the input here, and we get the output from the sigmoid. Okay. Now again, why the entire sum is not going and only a part of it going there? You can see I'm sending only the upper bits here. So maximum width minus whatever is the size of so-called sigmoid. Because again sigmoid is again implemented as a memory, and I can define what is the depth of that memory. The more deep it is, the better precision I will have, but more resources it will utilize. So here I have written sigmoid size is 5. That means the size of sigmoid memory is only 2 to the power of 5, 32. That's why in this MIF file you can see only 32. So if you increase that depth, you will have more accuracy. Okay, so this guy has only 32 locations available, but my sum, its total width is 2 times my total data width, which is like 16 here. That is the total data width for our fixed point representation. Again, you can change it. So you cannot directly send this entire 32 bits to the sigmoid. It won't work, right? Because those many locations are not there. So what we need to do, we need to drop all the lower bits and send only the most significant bits. And that is what is done here. So starting from the most significant bit, only the upper sigmoid size, those many bits we are sending. This style we have used before. This slicing in Verilog. This is how we do it, and we get the output. Okay, so we have the output here. So this is the basic implementation. Sigmoid, how it is done, I will explain in next tutorial, but I have you have an overall idea. So main takeaway is, irrespective of number of input, we make them sequential. We send them only one by one for getting better timing performance, as well as to reduce the resource utilization. That is one takeaway. And the weight values, we generally use a distributed bus, a shared bus, so that all the neurons are hooked up to the same bus. And by controlling the configuration layer number and neuron number, I can address a particular neuron to send the weight value to that particular neuron. Okay, so that's another takeaway. And whenever you write memory, you use the output in sequential format so that it will get implemented using block RAM instead of distributed RAM. Here you can see I'm not using sequential, I am using assign statement for this so-called the sigmoid ROM, which stores the sigmoid value. And because of this sigmoid memory won't be implemented in block RAM but in distributed RAM. But the size of the sigmoid memory will be quite small, 32 bit, 32 deep or 64 deep. So it is actually better to use distributed RAM, because block RAM, the smallest block RAM is 18 kilobit. So even if you are not using 18 kilobit, the remaining part becomes unused. So it is better to use distributed RAM for this activation function, but for weight values, it is better to use block RAM. Okay, so these are the main takeaway. Now the minor control signal you can try to read and understand. If you have any doubt, please ask me in the comments. I will try to replay. Most of them are to manage the pipeline delay, because we have one pipeline delay here, then one pipeline delay here, one pipeline delay here. So our valid signal has to be delayed accordingly. So that's what most of this logic is doing. Okay, so if they are not clear, please feel free to ask. I will try to clarify. So in next tutorial we will discuss more about the implementation of the activation function.